a battery? At its core, a battery is a device that separates positive charges from negative charges. The two sides of the battery are called terminals, and it does not let charges mix. How does it do this? Well, it uses up some chemical energy. If you've ever had a battery spill, there's this acid-like stuff inside, right? Here it is. And it uses up that chemical energy inside of the juice to push charges, all positives on one side, and push all the negatives on the other side. But these positives are all so close together. I mean, they want to go flying out and repel away from each other. But we can't just have positive charges spilling out of the battery. That wouldn't really be very good. So we put a cap on it. However, if you connect this battery to some wire, and then maybe your wire connects to a light bulb, now you have created a path that the charge can flow through, right? I mean, a positive charge, here's one positive, can finally be liberated. It's released. And it's getting repelled, right? This positive charge is pushed away by these positives. And it's getting attracted around this toward the negatives. So that positive charge is repelled away. It's getting pushed around the circuit. It goes through the light bulb. Let me actually show you what it does when it gets to the light bulb. Light bulbs have a special wire called a filament, kind of squiggly looking. If you shake a bulb to see if it's dead, you're trying to listen to see if the filament snapped. So now it's kind of dangling freely. So the positive charge goes around. It gets pushed through the filament. Oops. Oh, come on, positive. It goes all the way here and finally makes it back to the negative. But as soon as it arrives at the negative, the battery says, no, no, no. And it pushes this thing back over toward the positives. But pushing it together toward the other positives, that's hard. It takes a force. It takes energy and work. Where does the energy come from? You see this chemical juice down here in the bottom? It uses up some of the chemical energy in the juice, and now there's less useful juice. Right? Oops. Okay, so that's how batteries operate. We are going to look at the battery, and we're going to follow these positive charges as they move this way around the circuit. And we're going to make a table here. We're going to make a table. What happens outside the battery? What happens inside the battery? Outside of the battery, charge will flow from what terminal to what? Does it flow from positive to negative on the outside? Around this way, from positive to negative? Or do the positive charges flow from negative to positive? No, they don't do that. They're falling, right? From positive to negative. They're getting repelled. So outside, charge flows from the positive terminal to the negative. But once the charge finally makes it all the way around, let's get this positive charge here. Once it's on the outside of the battery, it's not inside the battery. Once it finally goes back into the battery, it flows from the negative terminal back to where it belongs, back to the positive. So inside the battery, it goes from the negative terminal to the positive. What about the field lines? Let's think about this. We're going to make an analogy to a positive plate and a negative plate. Field lines, we remember, point from positive to negative. So on the outside, the charge has finally been liberated. It's getting away from its other positives, and it's going toward the negative. So it's going with charge flows with the field lines. But once that positive charge gets back to the battery, once it gets over to here, it moves back over to the positive side. In other words, it's like, if we look at the uniform field down below, it's like it's getting pushed back this way. So once it's back inside, it moves against the field lines. Okay. Oops. So if that's true, the work by the electric field, is it positive inside the outside the battery, or is it negative outside the battery? Where does the electric field do positive work? The field does positive work outside the battery and negative work inside the battery. Why is this? Let's look. There we go. It's a little better. Okay, well, when the charge is flowing from the positive terminal, it's finally liberated. It's on the outside of the battery. It's liberated, and it goes toward negative. The force and the distance are in the same direction. It's flowing this way. There's the distance, and the force on our charge, well, it's a positive charge, so the force is always with the field lines. That's why it's positive work outside the battery. But if you change which way it's going, if you're inside the battery and you're moving the opposite direction, now the distance is opposite the field lines. So we have negative work. Almost done. The last one we want to put down, does the charge gain potential energy or lose potential energy outside the battery? The charge, is it gaining or losing? Outside the battery, it's moving from positive to negative. It's been liberated and it's able to fall back down to where it wants to go. So the charge loses electric potential energy. Outside the battery. But once it gets back in, once it returns to the negative terminal, it gets pumped back over with the other positives. In other words, here it is at negative, it's getting pushed back over to positive. So there, if it's going this way against the field, that means it would be gaining. It gains electric potential energy. Okay, so these are some really, really important traits. We need to memorize these. Whoa. And make sure they're right there at the tips of our fingers. Okay. Now there's one final thing to point out. Everything we have shown in this video so far is opposite of what actually happens in the real world. This is a place where the physics disconnects from the real world. Because, wait a second, this whole time we've been assuming that positive charges are the ones moving around the circuit. This whole time we've sort of kind of said, imagine that the negative charges are locked in place. It's closed off and they can't go out. They can't spill out. That's sort of what we said. And we said the positives, however, they are free to move. In the real world, the opposite is true. Protons make up positive charge, and you cannot move protons from one location to another very easily. You would have to cut pieces of the battery and move the battery, right? Electrons, on the other hand, they are the ones that can move freely. So the protons are essentially locked in place in the crystalline structure of the solid, and the electrons are the ones that can spill out. They are free to move around. So they get repelled and they move the opposite direction as what we've been doing this whole time. This is important. In the real world, real current, real charges, real current flow is negative. But in physics, we imagine that the positive charges are the ones that can move. So we say, okay, here's a positive charge spilling out, and the electrons are the ones that are locked in place. We call that, well, that's a convention that we use because we don't want to deal with negative signs, and it has some historical reasons, but we call that's just the current we use by convention, so we call it the conventional current. Conventional current. So the real current is negative. I don't really need the word flow there. Real current is negative. And conventional current is positive. That's the one that we actually deal with in our problems. And it saves us a negative sign. That's kind of nice. Conventional current is positive. And the thing we just need to know is that the real electron flow, the real current, is in the opposite direction. I'll just say is opposite the conventional current. So where the electron's actually going, they're going in the opposite direction. So this is kind of, it's good that we don't have to deal with both, because if you look back up, everything in this chart would change if we tried to think about the negative charges. We don't want to do that. We are always going to assume that positive charges flow. And that means everything in the table is reliable. We don't have to redo it or think about it differently.